This is our third video dedicated to Bessey Shuffle diagrams. Quick review. A shuffle S is said to be a Bessey Shuffle if and only if S preserves or inverts Bessey sequences. Recall, the Bessey sequences of order 8 are 1, 0, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 0, 1, 0, 0, 1. Also recall that the two sets of position values of importance to us are the following. The set A consisting of position values 1, 4, 6, 7, and A complement consisting of the position values 2, 3, 5, 8. Also recall, if position values stay within their respective sets after performing the shuffle, then we denote that outcome as follows, as indicated here. If inversion occurs, this is how we represent that outcome. And to quickly remind you, inversion occurs when the cards in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8. So it's as if the position values in these two sets get switched, and we call that an inversion. And to aid us in distinguishing between the elements in A and A complement, the digits here have been color-coded. Also remember that the two Bessey sequences of order 8 are 1, 0, 0, 1, 0, 1, 1, 0, in which the 1s are in positions 1, 4, 6, 7, and the 0s are in positions 2, 3, 5, 8. For the inversion of this Bessey sequence, namely what's written here, the 0s and 1s switch places. Consequently, there are only two possibilities for Bessey sequences of order 8, as listed here. So moving on to our next shuffle in this series, let's take a look at shuffle number 9, which is the top left shuffle on the diagram to the left. And we call this shuffle an even up jog. So as always, we'll begin with an ordered packet, 1 through 8, and then we'll perform our shuffle, record the outcome of that shuffle, and then describe the permutation involved, first in Cauchy's two-line notation, and then we'll rewrite that in cycle notation. Okay, so what is an up jog? Or in particular, what is an even up jog? Well, this is where you push forward or jog forward the even position cards. That's all you're doing. And then you strip those out. Now we have a left and right hand pile. And so for this first up jog shuffle, we will be stacking the left pile on top of the right, as indicated right there. Okay? So let's take a look at the new ordering of the packet. Okay, so we get 2, 4, 6, 8, 1, 3, 5, 7. That's kind of interesting. So let's take a look at what I've written up formally. So here is the two-line notation in which I've indicated that we now have the ordering 2, 4, 6, 8, 1, 3, 5, 7. Now we can rewrite this in cycle notation as follows. 1 goes to 2, so I have an arrow from 1 to 2. 2 goes to 4. 4, where's 4? 4 goes to 8. 8 goes to 7. And 7 goes to 5. And finally, 5 goes to 1. So it wraps back around. So we have a very large cycle, larger than the ones that we've seen in the past. This is a 6 cycle. Now for the remaining values, what happens? Well, we have 3, which goes to 6. And 6 goes to 3. So that cycles around. So we're looking at a 2 cycle, or in other words, a transposition. Now if we color code the cycle notation of our permutation, we obtain the following. So remember, 1, 4, 6, 7 have been color coded black. 2, 3, 5, 8 have been color coded red. So we have black 1 being sent to red 2, which is sent to black 4, which is sent to red 8, which is sent to black 7, which is sent to red 5, and that wraps around and gets sent to black 1. Over here for the transposition, we have the red 3 being sent to the black 6, which gets sent back to the red 3. So as our color coding makes clear, each value gets sent to a value of the opposite color. And when that happens, inversion occurs. So what this means then is all of the cards in positions 1, 4, 6, 7 get moved somewhere to positions 2, 3, 5, 8. So that's what we mean by an inversion. Now in terms of Bessey sequences, using the digits 0 and 1, if we start with this particular Bessey sequence and perform this shuffle, we should expect the inversion of this sequence to occur. So why don't we just quickly demonstrate that. So I'll go ahead and do an evens. Even positions are being moved forward, even position cards, strip those out, and then left on right. So it should now be the case that we're looking at 0, 1, 1, 0, 1, 0, 0, 1. And we are. So our original Bessey sequence was inverted. Also, I should point out that we're looking at a 6 cycle. And I believe that's the longest cycle length that we've seen thus far. So in particular, what this will mean is it will take 6 applications of this particular shuffle to reset the packet back to its original order. So 6 of those are needed. Now it is true that during those 6 shuffles, 3 and 6 will be bouncing back and forth between each other. But by the time you perform 6 shuffles, 3 will be sent back to 3, and 6 will be sent back to 6. So it truly will return the packet to its original order. Okay, well let's go ahead and take a look at the Bessey Shuffle diagram. Top left here. Now we've seen one similar to this. In fact, this is the inverse of 3. So in our very first video in this series, we saw this very graph except for the arrows being reversed. So if you take a look at Shuffle 3, it'll be exactly this diagram here, but the arrows will be going in the opposite direction, which of course means that if we perform those 2 shuffles in succession, they undo each other. Okay, so why don't we just quickly step through this. 1 goes to 2, so down here. 2 goes down here to 4. 4 goes up to 8, right there. 8 goes to 7. 7 goes to 5 down here, and then 5 goes all the way back up to 1. So that completes that cycle. So that is a cycle of length 6, and it's also an orbit. So the numbers 1, 2, 4, 5, 7, and 8 are all in the same orbit. They just get moved around among themselves. And then because we have a single transposition right here, 3 and 6, we'll get a double arrow between values 3 and 6. So for each time you perform that shuffle, 3 gets sent to 6 and 6 gets sent to 3. So they just switch places. And of course, if they switch places 6 times, they're back in their original locations. And up here, we've noted the fact that inversion has indeed occurred. Now, Shuffle 10 involves an even up jog as well. So if we begin with our original packet of 8 cards that have been clearly numbered so that we can keep track of the individual positions of these cards, performing the even up jog, so that's the same as the last shuffle, Shuffle 9. This time we strip these out, but we stack right on top of the left. Well, what does that give us for our new ordering? We get a 1, 3, 5, 7. Sorry, I'll move that over. 2, 4, 6, 8. And with a little bit of thought, you probably could have anticipated that that would happen. We've just switched the two halves that we had earlier after shuffle 9 was applied. Okay, so if we write the Cauchy two-line notation for a permutation, we obtain the following. 1, 3, 5, 7, 2, 4, 6, 8 is the new ordering. That can be converted to one-line notation, in other words, cycle notation. So 1 is a fixed point, 1 goes to 1. 2 gets sent to 3, 3 gets sent to 5, and 5 gets sent to 2. So it wraps around. So that completes that cycle. It's a 3 cycle. Similarly for 4, 4 gets sent to 7, 7 gets sent to 6, and 6 gets sent to 4. So it wraps around. So that's a second 3 cycle. And then we have just one more fixed point. Whatever's in position 8 will stay in position 8 regardless of how many times you perform that shuffle. Okay, so that's kind of fun. So positions 1 and 8 are fixed points. And then all of the other cards in the middle are kind of moving around among themselves in some fashion. In fact, in the way that we've just listed here. Now, if we color code the position values, we obtain the following. Remember, position values 2, 3, 5, 8 are color-coded red. Position values 1, 4, 6, 7 are color-coded black. So we can readily see that inversion does not occur. So the cards that originally began in positions 1, 4, 6, 7 stay somewhere in that set of position values. Similarly, for cards that originally began in positions 2, 3, 5, 8 stay within that set of position values. And that's what we've written here. So relating this to our Bessey sequence involving zeros and ones, since inversion does not happen, if we perform this shuffle, we'll get exactly this form back. In fact, why don't we just quickly show that? Okay, so we're going to do an even up jog. So you push forward the even position cards, strip those out. Now we're stacking right on left. So the claim is that we'll get back to the form 1, 0, 0, 1, 0, 1, 1, 0. Okay? Now it is true that the ones are moving around among themselves except for one of them. Can you think through which one is going to stay exactly where it is? It's the first one, right? Remember, we have two fixed points. Whatever's in position 1 stays in position 1. Whatever's in position 8 at the beginning stays in position 8. Similarly, for the zeros are being permuted among themselves with the exception that the last 0 here, which is in the 8th position, stays exactly where it is, or in other words, gets returned to its original location. And if we look at our graph here, top row on the right, this is the Bessey Shuffle diagram that goes with an even up jog in which we stack the right pile on top of the left. We can see our fixed points right here, 1 and 8, they don't go anywhere. And then 2, as we can see here, gets assigned to 3, gets sent to 3, 3 gets sent to 5, 5 gets sent back to 2. So we have a little 3 cycle. We also call that an orbit. And then if we go to 4, we see that it's sent to 7, 7 is sent to 6, and then 6 is sent to 4, completing that 3 cycle. And that's also an orbit. Those values are just moving around among themselves according to the direction of the arrows in the diagram. And notice this time we're looking at a shuffle that has order 3. Now when we say a shuffle has a certain order, what we mean by that is you need to apply that shuffle that many times, the order number of the shuffle, to return the packet to its original order. Okay, so since we're looking at a product of 3 cycles over here, that means performing this shuffle 3 times resets the packet to its original order. Moving on to our next shuffle, which is called a Moge, M-O-G-E shuffle. It comes in 2 varieties. an over, under, and an under, over, as you will see. So this is a very popular shuffle and can be used in a variety of settings to, quote, randomize the cards in a way that many of the other shuffles do not. Okay? So it's a great shuffle to be aware of and understand, at least to some degree, what this shuffle is doing to the ordering of the cards. Okay, so let's go ahead and see what this shuffle is doing. So as always, we begin with an ordered packet 1 through 8, and then we will look at the effect of the shuffle on this ordered packet. Okay, so what is a mange shuffle? Well, you push over the top card. Now this is an over-under, so what that means is the next card right here goes over this one. The next one now goes under, then over, under, over, under, over. So that is a mange over, under. So what is the new ordering that we get? Well, it's 8, 6, 4, 2, 1, 3, 5, 7. So if we come down here, that's what I've written up for the Cauchy 2-line notation for our permutation. It's going to be 8, 6, 4, 2, 1, 3, 5, 7. And we can convert 2-line notation to 1-line notation, which is also called cycle notation. Okay, so let's step through that quickly. So 1 gets sent to 8. Where does 8 get sent? 8 is sent to 7. Where is 7 sent? 7 is sent to 5. And then where does 5 go? 5 is sent to 1. So it wraps around. So we're looking at a 4 cycle here. Okay, what about the remaining position values? Well, 2 gets sent to 6. 6 gets sent to 3. 3 gets sent to 4. And then 4 gets sent to 2, which wraps around and completes that cycle. So it looks like we have 2 cycles of length 4, or 2 4 cycles as we call them. Okay? And that actually accounts for all of the position values. All 8 positions are now accounted for. Now, if we color code this, we obtain the following, which is quite interesting. So we can see here that inversion has occurred this time. Remember, the position values 1, 4, 6, 7 are color-coded black. The position values 2, 3, 5, 8 are color-coded red. And so we can see that there's an alternation of the colors once they've been color-coded correctly. So what this will mean then is what was in position 1, so black 1 goes to red 8 goes to black 7 goes to red 5. This wraps around and goes to black 1. Red 2 goes to black 6, which goes to red 3, which goes to black 4, which gets sent to red 2. So inversion has indeed occurred. Each value gets sent to a value of the opposite color. So because inversion has occurred, we should not be surprised by the effect of this shuffle on our standard Bessey sequence if we begin with 1 as the leading digit. So if we begin with a Bessey sequence of 0s and 1s and perform this shuffle, we will get the inversion of this sequence. So why don't we just quickly show that. So a mange over under, you push over the top card. The next one goes over, under, over, under, over, under, over. Okay, so has inversion occurred? Well, it looks like it has. We had 1, 0, 0, 1, 0, 1, 1, 0. Now we have 0, 1, 1, 0, 1, 0, 0, 1. Now, unlike the last shuffle where we had a couple of fixed points, that does not happen here. So here we can genuinely say that the cards labeled with 1s will genuinely move around among themselves each time you shuffle a packet of 8 cards, and the cards labeled with 0s will move around or permute among themselves each time you perform this shuffle. Okay, so there's no fixed points. Cards are moving around. Now, it is true that this is a shuffle of order 4, right? So if we perform this shuffle 4 times, it resets the packet to its original order. Okay? Now let's go ahead and take a look at the graph, because this is a very chaotic looking graph here. So we know that 1, so here's 1 goes to 8, which goes to 7, which goes down here to 5, which goes up here to 1. And that completes that cycle, that 4 cycle. That's also called an orbit. And then 2 gets sent to 6, which gets sent to 3, which gets sent down here to 4, and then 4 is sent to 2, completing that cycle of length 4. That's also an orbit. Now, if you look at the messy nature of the movement of the cards in these various positions, it should be rather surprising, as we'll see, both in the over-under and under-over are Bessey Shuffles, meaning they preserve or invert, as is the case here. Inversion occurs. They preserve or invert Bessey sequences. And then I have a note down here that this particular shuffle is the inverse of shuffle 19 that we'll look at in a future video. And finally, the last shuffle for today is the mange under-over. So let's go ahead and show you how this one works. So we begin with an ordered packet, as always, 1 through 8, so that we can keep track of what's happening to the different cards in these 8 positions. Okay, so the mange under-over, well, it begins the same as the over-under. You just push over the top card. Now this time, this card over here goes under the one on the left. Next one goes over, under, over, under, over, under. Okay, so that is the mange under, over. Okay, and as you would probably guess, you get a different ordering. You really do for this, and that's why the shuffle diagram is so different. Okay, so it looks like we get an ordering of 7, 5, 3, 1, 2, 4, 6, 8. Okay. Well, is that what I've written down here in Cauchy's 2-line notation? Well, it should be 7, 5, 3, 1, 2, 4, 6, 8. And that can be converted to cycle notation as follows. We can see here 1 goes to 7, 7 goes to 6, 6 goes to 4, 4 goes to 1, so it wraps around. So we have a completed 4 cycle. Now what about 2? 2 gets sent to 5. And 5 gets sent to 2, so that gets closed off as a cycle. So we have a transposition there, 2, 5. And then whatever's in position 3 will stay in position 3 after the completion of this shuffle. So 3 goes to 3, so we have a fixed point, or a single cycle, sometimes called a 1 cycle. And the same thing is true for position 8. Whatever starts in position 8 will end in position 8. It won't go anywhere in the end. It will be returned to its original location. Okay, so we have a 4 cycle, a transposition, and 2 fixed points. And maybe as a reminder, we normally don't include 1 cycles in the cycle notation of permutations, as long as it's clear as to what the size of the set is that you're working with. Okay, so if we know or remember that we're working with 8 objects, we can drop these 2 1 cycles in our representation up here. Now we include them in the color coding just because it will be helpful to see what's going on. So now if we color code our permutation expressed in cycle notation, we'll clearly see that inversion does not occur because 1, 4, 6, 7, those position values are all color-coded black, and each of them is sent to another black value. Here, the positions 2, 3, 5, 8 are color-coded red. And so we can see that red 2 gets sent to red 5, which gets sent to red 2. And then we have a red 3 being sent to itself, and a red 8 being sent to itself. So here we can just conclude each value gets sent to a value of the same color. So what that means then is if we perform this shuffle on our quintessential Bessey sequence of 1 0 0 1 0 1 1 0, we get back to that original form. Okay, so here we're doing an under, over, under, over, under, over, under. So we're going to get back to a 1 0 0 1 0 1 1 0. Okay, and then you can just make note of the fact that all of the ones are moving around among themselves, actually, with no fixed points, because that's what's happening here. Because the ones are in positions 1, 4, 6, 7. Those position values stay within that set of values, okay? Now that's not true for the zeros, because the zeros here are in positions 2, 3, 5, 8. Now it is true that the one in the second position and the one in the fifth position, this one right here, those are getting switched. They switch places each time you perform this mange, under, over. They just switch places back and forth. Now, the zeros in position 3 and 8 are fixed points. So they are simply returned to where they started. So they do not get moved to new locations once that shuffle is complete. And then taking a look at our graph here, bottom row on the right, we can see that the 8 and then down here the 3 are fixed points. We can also see that inversion has not occurred, which is what we just pointed out. And then if we follow our diagram right here in cycle notation 1 7 6 4, so that means that 1 gets sent to 7, which gets sent to 6, which gets sent to 4, and 4 gets sent back to 1. So that is a 4 cycle. It's also called an orbit. And then we have 1 transposition. So 2 gets sent to 5, which in turn gets sent back to 2. So those just switch places every time you perform this shuffle. So as we look at the cycle notation of this permutation, we can readily conclude that this shuffle has order 4. If you perform this shuffle 4 times, it returns the packet to its original order. Okay, very good. Well, let's show you an application for all of this, since we haven't shown you one yet. So what we're going to do is I'm going to show you an application that I hope will kind of convince you that 7 is a lucky number. 7 is a very lucky number. And people have heard that before, and many believe that that is indeed the case. So I'm going to try to convince you of that with this little exercise here now. Okay, so as you can see, I have 4 3s and 4 4s. Okay, so I'm going to begin just mixing these. So I'm going to put them down into piles. Now, if you were here, what I would do is I would begin dealing until you tell me to stop. And maybe you tell me to stop there, maybe stop there, stop there. One more, okay. Okay, why don't we do another one of those? We can do as many of these as you like. Tell me when to stop. Stop, okay. Stop there. Stop just right there. And then, okay, very good. Would you like to do one more of those? You would. Okay, tell me when to stop. Stop there, okay. Stop after just one. Stop there, okay, very good. Okay, and then we're just stacking from right to left. Okay, that's quite a bit of mixing to scramble these initially. And then what we're going to do is we're going to put them out kind of in a triangle configuration, which is fun to do actually. And then we'll just stack them in opposite order, which will really help to mix these cards. And now we're going to perform each of our new shuffles here today. And so if you were actually here, I would have you just randomly choose an order for each of these. Now the reality is you can actually perform any one of these shuffles as many times as you like and in any order that you like. That is the amazing thing about Bessey Sequences and Bessey Shuffles. Okay, so if you were here, maybe you would choose to do the last one first. So you might say, do shuffle 12 first. So okay, let's do that one. That's the mange, under, over. So you start by putting that first card under. What would you like next? Shuffle 9? Okay, so that's the even up jog in which we stack the left pile, this one on top of the right. What do you want next? The mange over under. Okay, we'll do that one. So you push over the top card. Now this one goes over and then under, over, under, over, under, over. Okay, and that leaves our shuffle number 10. That's an up jog as well. But this time we're going to stack the right on top of the left. Okay, and I really wish you were here because I would have you ask for more of these if you would like. Maybe you want 2 more applications of one of them or something, or 3 of them done, or whatever it might be. So why don't we just do 1 more of these? Which one would you like? And I'm just kind of pretending to maybe guess what you would guess, but it actually wouldn't matter. You would genuinely have a free choice in this. Okay. Oh, you like the mange over under because of its crazy looking graph? Okay, well, we'll do that one more time. So this is where you push this one into your other hand, and then it's over under we're looking at shuffle 11. So it's over, under, over, under, over, under, over. Okay. Well, I think if you do those shuffles, several times, that will convince virtually anyone and everyone out there that no one could possibly know the ordering of these cards. And that is truly a fair statement. For one thing, I could not know ahead of time what order you would choose and how many times you would have me do the different shuffles. And we did that randomization at the beginning that kind of mixed up the cards where really none of us could know exactly where we even started. Okay? So let's go ahead. What I'm going to do a little differently than we've done in the past, with some of the previous videos, what we've done is we've done the Klondike Shuffle to create pairs, and we could do that here. That would work just fine. But this time I just dealt out into 1, 2, 3, 4, into 4 piles. So what are we looking at here? So why is it that some people claim that 7 is a lucky number? Well, I don't know. Let's just see what we find. Oh, that's interesting. So those add up to 7. That's kind of fun. What about these? Those add up to 7 as well. There's no way this is going to add up to 7. I mean, surely that... Oh, man. How in the world? I think we have proven beyond a shadow of a doubt that something special is going on with the number 7. Okay, so how does this one work? So let's just quickly show you how it works. Okay, so we began with this kind of arrangement. I don't know if the 3s are in the same ordering they were at the beginning and the 4s. It actually doesn't matter. Okay, so what I did was to give the impression that we're beginning to really just mix these cards and you're having a say as to how we mix them. What I did was I performed, I think it was 4 or 5, what are called the first shall be last and the last shall be first. So how this works is you just begin dealing the cards until the spectator says stop. So maybe they say stop there, and then you just keep dealing until they feel the urge to say stop, okay? Stop there, and then you put down the last card. Now it's called the first shall be last and the last shall be first, and it's because of the stacking. So the very last card dealt is the one over here, okay? So the first shall be last, the last shall be first. So you just stack in opposite order to which you've dealt them out. Why don't we do 1 more of these? So you just start dealing till the spectator says stop, and then you deal into another pile. Maybe they say stop there, maybe they say stop there, and then we have this 4th pile over here. So the first shall be last and the last shall be first. Now it ends up that you can do as many of these as you like. Why is that? Well, each of those shuffles of dealing them out and then stacking from right to left is actually a packet reversal. You're just reversing the order of the cards. That's all that does. Now, for most observers, it would appear to be doing much more than that, but that's all it's doing. It's just reversing the order of the cards. Now, if you do that shuffle an even number of times or an odd number of times, it actually doesn't matter. Now, if you do it an odd number of times, what will happen is the threes and fours will switch places. Well, that will not in any way undermine what we hope to accomplish. So it doesn't matter if it actually reverses the order of the cards. What is important for us is that these cards are still in blocks. One block of fours and one block of threes. Okay, that's all we need. And then from there, I use something called the triangle deal. And this is just a very clever way to convert a structure of the type that I just showed you into a Bessey packet or Bessey sequence. Okay, so this is a really fun way. And then maybe I did it a little fast, but you're dealing them out clockwise into a triangle, clockwise. And then when you're done dealing all of them, you pick up the pile that you created first in your dealing, and then you stack and counterclockwise. So just the opposite order. And that is guaranteed to do something very special with the original packet. It will convert it to a Bessey sequence relative to card values 3 and 4. Okay? So what that means then is for it to be a Bessey sequence, we should see something like, we see a 3 here, which is fine. So we should see 3, a couple of 4s, and then a 3, break. And then we should see a 4, a couple of 3s, and then a 4. So it's like having 1, 0, 0, 1, 0, 1, 1, 0. So this is of the right structure type so that the shuffles I'm showing you today, which are Bessey shuffles, will preserve this Bessey organization of the cards. Okay? So if you go through and perform any of these shuffles as many times as you like, it won't harm this. Now, it may invert it, right? We talked about that. So on some of these, so for example, the even up jog in which we stack the left pile on top of the right, that will actually invert the packet. So the 3s and 4s switch places. That's all that means. So that's shuffle 9. Shuffle 10 does not invert the packet. Shuffle 11 does invert it. And then shuffle 12 does not invert it. Okay? Now, for what we hope to accomplish, it doesn't matter whether the packet gets inverted or not. So that, which is wonderful, because that means you don't even really have to keep track of whether the packet has been inverted by a particular shuffle. Now, if you were to keep track of that, so for example, if you were to just peek, like right here, if you were to peek the bottom card here, you would know that the bottom card is 4. Okay? Now, if you've kept track of whether or not your shuffles are inverting or not inverting, if in the end you know that this should not be inverted, so what that means is that bottom card will still be 4. So the organization of the cards will still be of this kind: 3, 4, 4, 3, 4, 3, 3, 4. Whereas if you know that the packet has in fact been inverted because of the shuffles that you chose in this list of 4, then what that means is the bottom card will now be a 3. And so that would just invert it. An easy way to kind of make it look like it's been inverted is to just reverse the cards. So now we would have a 3 at the bottom, and that would tell us that we're looking at 4, 3, 3, 4, 3, 4, 4, 3. So that's just an extra credit insight I thought I'd give you. We don't need any of that for what we did in that performance. I just want to point out that inversion sometimes occurs, sometimes doesn't. Depending on what you hope to accomplish with the packet, you may or may not need that information to finish in the way that you like. So in the kinds of applications I've been showing you, we haven't really worried about whether inversion happens or not. Okay, so anyway, so at this point, what I did was I just dealt out. In fact, let's just show you that, have you think through this. Okay, so this is guaranteed to be a Bessey sequence, regardless of which of the 4 shuffles you use. Okay, so we'll have something like this: a 4, 2 3s, a 4, and then a 3, 2 4s, and a 3, or the inversion of that, where you start with a 3 here and a couple of 4s and so forth. Okay, so think about this. When I dealt it out into 1, 2, 3, 4, into 4 piles, what is that going to do? Okay, so why don't we just do it face up? Okay, so this is the top card. Okay, but I'm gonna deal it face up so you can see it. Okay, so if I did 1, like pile 1, pile 2, pile 3, pile 4. Now I'll repeat that. Pile 1, pile 2, pile 3, pile 4. And you can see what's happened. What's happened is exactly what we wanted to happen. We're looking at pairs of cards whose values add to 7. And that's guaranteed to happen. So you can deal out into 4 piles like I've done in this particular video, or you can do the Klondike Shuffle and create pairs that way, which is the way that we've done it, I think, up to this point in this series. So those are just 2 of many ways, actually, to create pairs of interest to us. The pairs of interest here are ones whose values add to 7. Okay, so I think we'll stop there. There's much more I can show you, but I don't think it would be helpful to overwhelm you with too much information here. We have many more videos in this series in which I can continue to add insights and understanding to how you can use all of this to create your own amazing mathematical card effects. So thank you for watching.